We recently visited a conference for industrialists, engineers, and scientists interested in chemical processes for the manufacture of a wide range of products. We asked a small cross-section of delegates to tell us about measurements they need to create better processes and products. Let's hear what they said.
One of my key interests for quite a long time has been industrial process tomography and creating solutions as well for people in industrial scenarios who have issues of measuring things that are quite difficult to measure otherwise. So we're looking at the idea of measuring things inside processes. So the basic technology looks inside these things, just like body imaging technology in the medical domain does for the human body. Sadly, human beings are quite simple in terms of how we can image them. We're just really mostly water and bones, quite easy to image, but most industrial processes are quite difficult to image. So we have the problem of looking inside pressure vessels, finding very complex multi-component mixtures. So one of my interests has been in addressing these problems and issues. And we started out quite a long time ago now using a single energy level to do this in electrical or ultrasound or whatever. And we found that we can do that quite well. And so we've had quite a lot of successes in simple processes, in pipelines with a simple liquid flowing through, in mixing vessels where we've got one form of material that's mixed into another one, where one gives us a very good contrast level that we can see using the word see in terms of our imaging technology. So those are successes, but we found that where we have mixtures of several things, these simple single energy systems, what I call first generation systems, don't work quite as well as we'd like. So my focus for the future, looking for priorities, is to try to develop multimodal and multi-frequency, multi-energy systems. And one of the technologies that I've been working on is called spectrotomography, that combines spectroscopy with tomography. Lots of ographies and ologies there for us. And so by doing this, we can actually look spectrally at the material and work out what the material is, and we can use our tomographic aspect to work out where that particular material is in its location. And combining these two together gives us the what it is and where it is. And also the tomographic system tells us when it is as well. So we've got all of these things together. We can recognize where things are in processes, and we can also say what they are. So we can answer a lot of the questions that our colleagues in industry have about how their processes are working. Is the mixture working properly? Is the pipeline transporting materials we'd like? Is the reactor working? Are these processes delivering the sort of utilization level that we'd like? Are we lowering our emissions? Are we making our process as efficient as possible?
I'm really interested in what happens inside industrial equipment, which usually, of course, has metal walls, usually full of opaque materials. So it's very difficult to investigate what happens inside equipment unless you've got some kind of special technique. And the technique that I make a lot of use of is radioactive particle tracking, specifically using positron-emitting radioactive tracers. So I'm interested in interacting with other people who have other techniques that would enable me to see the things that I can't see, because I can follow the trajectories of individual particles within equipment and individual elements of fluid, but I don't know what's happening elsewhere in the vessel. I don't get directly the density variations in the vessel and things of that kind. So I'm interested in interacting with people who have other modalities, as they're called, using X-rays or perhaps electrical techniques that would complement the kind of thing that I'm interested in. So that's one area of collaboration that I would be interested to start. The other one is that it seems to me that there are a lot of mathematical techniques that we could all make use of in the imaging community. So I'm interested in following the trajectories of particles. There are other ways of doing that, but I think there's a common set of mathematical principles that you can use to follow trajectories. And it would be interesting to work with mathematicians and with other enthusiasts for tracking techniques to develop a common selection of mathematical techniques that we could apply together to the kind of problems that we're interested in.
One of my major research areas is looking at electrical process tomography for monitoring manufacturing processes of formulated products. So what I've been looking at over the past years is applying electrical process tomography to look at multi-phase systems to generate images and data around things like local concentrations and local mixing rates. One of the things we've been doing recently is actually taking this technique and trying to get information about the microstructure. So for instance, we can look at property changes of material, of things like viscosity, when we're actually using the electrical process tomography. So in the future, one of the main areas that we need to go into is seeing how we can tie this measurement up with control, so we can look at multivariable control for our actual manufacturing processes.
I work in bioprocess engineering, and I have been interested in looking at the inhomogeneities that occur during fermentation. And this is particularly important as the size of the fermenters increase. And then by definition in large tanks, you have non-homogeneous systems. And of course, these inhomogeneities cause a lot of problems and need to be understood in order to optimize the microbial or cell processes. For instance, there are gradients in oxygen, dissolved oxygen, there are gradients in pH, could be gradients in temperature, or even in some of the sources of carbon, for instance. And then usually these big fermenters have different conditions and are inhomogeneous in terms of the space and in terms of time. There's a great need of sensing this process in order to understand them better. And as we understand better this process, we could propose better strategies for improving yield or productivity of the products. We have to deal with the inhomogeneities, but we have to know the extent of that inhomogeneities in large bioreactors. And this even can exist in small fermenters which are dealing with very viscous fluids. I have worked with biopolymer producing bacteria and mycelial biomass, which increase considerably the viscosity of the system. And then even in small tanks, then the inhomogeneities are present, and there is a need, as I said, to understand these inhomogeneities by sensing all kind of process condition throughout the fermenter and throughout the fermentation process. I think there is a wide opportunity for sensing and developing new techniques and new probes in order to get as much as information as possible in order to produce better products and more economical processes.
Our company is mainly based in instrumentation. We supply tomography systems, mainly capacitance and resistance. I've been working for the last 5 years in the automation industry, so I'm quite happy to work with the leader of the tomography systems. I work with a wonderful team of engineers. Our technical sales department, marketing and research and development colleagues are wonderful. They are always there to help, and we always customize our solutions for the customers. Since I've been working on ITS, we never had a system similar to other, so we all make personalized systems. The main goal working on ITS is seeing a great successful process and giving the customer all the information they need. Working for ITS is a great success due to we always personalize and customize our systems. One of our biggest success is working for a dredging company, one of the biggest in the market. We are replacing all the gamma units, which is really good for the environment and really good for us because it helps developing our technology. At the same time, we have our focus in other industries as pharma, dairy, chemical companies. Basically, we don't have any limitations because tomography is really flexible.
My research interest is in multi-phase mixing, so I look at gas-liquid mixing. I use electrical resistance tomography to monitor mixing times and gas holdup distribution, and then I use this data to compare it with the power data to help get the mass transfer coefficients or the mass transfer data. I've been doing this for the last 2 years now and found it really interesting. A lot of the work in the past has been done with homogeneous regime, whereas industries are actually using higher superficial gas velocity. So at large scale operation, we have heterogeneous regime. So my main research aim was to look at heterogeneous regime because there is not a lot of work done in literature.
I have been looking into the dispersion of viscous oils in water using either steered vessels or rotor stators. So we're talking about mechanically agitated devices. I'm looking into the droplet size distribution, which can become very bimodal for viscous dispersed phases as these become bimodal. And the common approach is to either measure the maximum droplet size or the outer mean diameter. Well, during my research, I've been taking a step further, and actually I've been trying to describe the whole distribution. So the type of instruments I use for my research are laser diffraction particle size analyzers, such as a Mastersizer 3000, which require me taking samples. We're not able to analyze this during the emulsification itself. So far, I don't believe any instrument can do that, as we're talking about droplets that vary in size 3 orders of magnitude. So no video probe is capable of doing that in real time. And I believe it would be very interesting if such technology was developed in the future. And this will also allow us to get into the physics of the process, as we would be able to elucidate how the droplet breakup mechanism occurs, as well as how coalescence, which is even a more complicated problem.
So I'm working with electrical resistance tomography to try and expand its application. I'm currently working with rheology, so measuring the velocity within a pipe and then correlating it to rheology. So this has not been done before, and it's an advancement in process technology. This allows us to measure rheology inline and almost in real time. So I've been working with electrical resistance tomography for 18 months now, and it definitely has its benefits. It's a robust technique and it's expanding all the time, especially with respect to rheology. In a pipe, it's relatively easy. However, I want to expand to vessels. Now this comes with complexity, so obviously you have flow fields which are always more complex and you can't relate it to rheology. So one thing I want to do in my research is improve this and eventually develop a fingerprinting tool for rheology within a vessel.
We can classify and examine these various pressures and drivers in more detail. Here, the red circle represents business pressures which seek higher bottom line benefits. Our multi-dimensional sensing technology provides key insight to provide flow information to enhance process performance, leading to a higher utilization of product quality and safety. The green circle represents fiscal and societal pressures to reduce impact on the environment. Our technology provides advanced flow information leading to reduced waste and impacts. Finally, the blue circle represents pressures to reduce energy consumption and global warming emissions. Enhanced flow process information aids efficiency gains and reductions in energy usage and emissions. We've been working with images. As any schoolchild knows, mixing red, green and blue light gives white light. This analogy illustrates the resulting red, green and blue potential flow process improvements we gain through enhanced information from process sensing technology.
It is clear that the better our sensing and measurement technology is, the better our products can be.